The focus of this video is an application of exponential equation where we look at carbon dating. So here we have the half-life of carbon-14, which is used in carbon dating, is 5,730 years. An artifact is found to have 45% of its original amount of carbon-14. Use this information to find the artifact's age rounded to the nearest year. Now what we want to start with is to reference the half-life formula with the half-life that we have for carbon-14 to find our value for K. So here we have our half-life formula, and it is telling us that the time in which we have our half-life is our 5,730 years. So I have 5,730 is the number of years to have half of what we originally had. So that's equal to the natural log of 1/2 divided by K. Now multiplying both sides by K and then dividing both sides by 5,730, we get K is equal to the natural log of 1/2 divided by 5,730. Now we could go to a decimal form and take it several place values out beyond what we want to round to. I'm actually going to carry it along in its exact form and then use everything at the very end in the calculation. So next up we want to remember our continuous decay formula, which is A of t is equal to A sub 0 times e to the kt, but we have just found in the previous line that k is natural log of 1/2 divided by 5,730. So that gives us our A of t is equal to A sub 0 times e to the natural log of 1/2 divided by 5,730 times t. And be careful that you write that k as a coefficient in front of the t, but that those two things are exponents on the base of e. So you have to be really careful when you're writing it from one stage to the next. Now what we want to find is the time required for the 45% of the original amount of carbon-14 to be present. Here's where it's important that you kind of make sure that you realize this is showing up each time you go through these. So what you're saying is the amount present right now at the time that it was found is 45%. Changing that to decimal is 0.45 of the original amount, and the original amount is that notation of A sub 0. So since that's what's presently in the artifact, we will actually replace that 0.45 times the original amount in for what is currently there. So on that left hand side of the equal sign. So I have 0.45 times the original amount is equal to the original amount A sub 0 times e to the natural log of 1/2 divided by 5,730 times t. Now every living thing has carbon-14 present, and so my original amount of carbon-14, as long as my artifact was made of something that when it was originally made was something that was alive, my A sub 0 will be 0. So we can divide both sides by A sub 0 because we're not dividing by 0. So then we get 0.45 is equal to e to the natural log of 1/2 divided by 5,730 times t. To solve this, we will go ahead and take the natural log of both sides since our base is e. So coming up to the right side over here, we'll have the natural log of 0.45 is equal to, well, the natural log of e to that exponent will just be that exponent. So we have the natural log of 1/2 divided by 5,730 times t. And that was from a property of when we're taking the log that base that matches an exponential expression, it simplifies to the exponent. Now remember, here we want to solve for t. So to solve for t, we will multiply both sides by 5,730 and then divide both sides by the natural log of 1/2. So I get t is equal to 5,730 times the natural log of 0.45 divided by the natural log of 1/2. Now it's time to get an approximate age for it, and we want the age to be rounded to the nearest year. So we'll start by calculating that through, and then when you round it to the nearest year, you get that the time is approximately 6,601 years for it to have 45% of the original amount of carbon-14. So that is the carbon dating process assignment of the age of that artifact.